This is the 8th video in a series covering abstract linear algebra. In the previous couple of videos, we covered vector spaces and subspaces of vector spaces and gave tons of examples. And now we want to look at a special class of functions from one vector space to another vector space called linear transformations. We'll look at a bunch of examples of linear transformations as well as prove some basic results regarding linear transformations. So let's get to our relevant definitions for this video. So let's suppose that V and W are vector spaces over the same field K. Then we say a function t from V to W is a linear transformation if it satisfies the following two conditions. So t of v plus w is equal to t of v plus t of w, and this is for all v and w in V. And then t of alpha v, so that's the scalar multiple of v by alpha, is equal to alpha times t of v. And this is for all alpha in K and all v in V. And I'd like to point out that a little more is going on here than it might seem. This addition here of v plus w is occurring within the vector space capital V, whereas this addition right here between tv and tw is occurring within the vector space W. And the vector addition in V and W might look quite different, as we saw in previous videos. And then furthermore, the scalar multiplication here is happening within V, whereas here it's happening within W. Again, the scalar multiplication might look different depending on the vector space. Finally, I'd like to point out that this thing right here, this condition I should say, means that T is a group homomorphism if we view V and W as abelian groups with their addition operation and forget the fact that we have scalar multiplication. Again, we did a little bit with groups and group homomorphisms earlier in the videos. Okay. So next, if T is bijective, so in other words, it is injective and surjective or one-to-one and onto, then it's called a vector space isomorphism or an isomorphism of vector spaces. And then we would often write V being isomorphic to W. So in shorthand, it's written like this. So an equal sign with a squiggle above. And we would read this as V is isomorphic to W. Finally, I'd like to define two subsets related to this linear transformation T. The first is the kernel, and we'll say that the kernel of T is equal to all V in V such that T of V equals 0. So it's everything mapped to the 0 vector in W. Let's notice that this is obviously a subset of capital V, given that it pulls out from vectors in V. Next, we have the image of T, and that's going to be all W in W, such that W equals T of V for some V in V. This is going to be a subset of W. Okay, so we're going to start this video by proving a couple of standard basic results and then do examples at the end. So our first proposition starts with an arbitrary linear transformation T from V to W, and we'll prove three things. So the first thing that we'll prove is that T evaluated at the 0 vector is 0. So this actually occurs immediately based off of the fact that we know T is a group homomorphism if we restrict to the addition, but we'll do it without kind of that assumption. This is maybe not really groundbreaking, but this is an important property if you'd like to prove that a certain function is not a linear transformation. Then it will often not map the 0 vector to the 0 vector. So like I said, this is often good for showing that something is not a linear transformation. Okay, so anyway, let's get to it. So let's take T evaluated at 0. And then maybe rewrite that as T evaluated at 0 plus 0, because 0 is the additive identity, but that's equal to T of 0 plus T of 0. But now we can subtract T of 0 from both sides, and that'll give us just immediately T of 0 equals 0. Maybe if we wanted to, we can add a 0 plus over here. So we're really just eliminating this t of 0 from both sides of the equation, leaving us with 0 equals t of 0. Okay, so that means we've proven this first condition. Now let's prove the second one, that the kernel is a subspace of V. And this one, as well as the last one, actually follows again, mostly from the fact that this is a group homomorphism of addition. We just really have to check that the scalar multiplication is preserved as well. But we'll prove both of them. Okay, so let's recall, in order to be a subspace, you must be closed under addition and scalar multiplication. So let's suppose that we have little v and little w from the kernel of t, and we have alpha from k. So we'd like to show that the sum of these two vectors is also in the kernel, and then the scalar multiple of one of these vectors with alpha is also in the kernel. So let's see. In order to be in the kernel, you must be evaluated to 0, just by the definition of the kernel right here. So let's look at t of v plus w. So since this is a linear transformation, we can write it as t of v plus t of w. But since v and w are both in the kernel, this is just the 0 vector plus the 0 vector, which is the 0 vector. So we see that if we evaluate v plus w with the linear transformation t, we end up with the 0 vector, but that's exactly what we need for v plus w to be in the kernel of t. So we've shown that the kernel of t is closed under vector addition. Now let's show that it's closed under scalar multiplication. So let's look at t of alpha times v, but that's going to be equal to alpha times t of v, but that is alpha scalar multiplied into the 0 vector. Because I've got multiplication here, maybe I'll put an arrow over 0 to show that it's the 0 vector, not the 0 scalar. But in a previous video, we showed that any scalar multiple of the 0 vector was the 0 vector. So we know that this is the 0 vector. But again, evaluating alpha v with t and getting the 0 vector is exactly the entry fee to say that alpha v is in the kernel of t. So we've shown that the kernel is closed under both vector addition and scalar multiplication, which is exactly what we need for this thing to be a subspace of V. So all that we need to do now is show that the image is a subspace of W. And we'll do that again by showing that the image is closed under vector addition and scalar multiplication. So let's go ahead and suppose, in this case, I'll call them W1 and W2 are in the image of T, and alpha is from the field K. Let's recall, what does it mean to be in the image of T? Well, that means that W1 is equal to T evaluated at V1, and W2 is equal to T evaluated at V2 for V1 and V2 in V. Great. So anyway, to get into the image, it means that you must be, well, the image of a certain vector from the domain. But now let's look at the sum of V1 and V2 and apply T. So if we do T of V1 plus V2, well, since it's a linear transformation, we get T of V1 plus T of V2. But then by this line right above, which is how we define V1 and V2, we get W1 plus W2. But then we've written W1 plus W2 as the image of an element from V, but that's exactly what we need for W1 plus W2 to be in the image of T. Okay, so we've shown that the image is closed under vector addition. Now let's show that it's closed under scalar multiplication. And we'll do that maybe by noticing that T of alpha V1 is equal to alpha T of V1. Again, because we can factor scalars out of linear transformations, but that's exactly alpha W1. But again, now we've written alpha W1 as the image of something from V, in this case, alpha V1. But that means that alpha W1 is in the image of T. So now We know that the image of t is closed under vector addition and scalar multiplication, but that's exactly what we need for this image of t to be a subspace of W. Okay, good. So I think we're going to prove one more result before we look through a bunch of examples. Now we've got a very important result involving the kernel and injectivity of a linear transformation. This is related to a similar result that we proved for group homomorphisms. And this result is so important that most of the time when checking if something is injective, you use this result. Okay, so let's look at the result. It says that t is injective if and only if the kernel of t is equal to 0. So in other words, the kernel of t only contains the 0 vector. Well, from the last result, we know that the kernel of t must always contain the 0 vector, but it could contain more vectors as well. Well, if it only contains the 0 vector, that means the linear transformation is injective. And when I said this was important, and we usually use this when checking for injectivity, what I mean is that if you have an idea that something is injective, you should probably show that the kernel is trivial, and that will prove the injectivity. That's the way to show injectivity, by looking at the kernel. Okay, so anyway, let's get to this proof. So let's start with this forward direction. So in other words, we want to suppose t, which goes from v to w, is injective, and we have v in the kernel of t. And I should say maybe before we get started, we already know that this set containing the 0 vector is a subset of the kernel of t. So really just we need to show that the kernel of t is a subset of the set containing the 0 vector. And then we've shown that they're equal by double containment. Okay, so we've got v is in the kernel of t, but that means that t of v is equal to 0. But from the previous proposition, we know that's the same thing as t evaluated at the 0 vector. But now we can apply injectivity to show that v is in fact equal to the 0 vector. But the 0 vector is definitely an element of the singleton containing the 0 vector. So let's see where we started. We started with v is in the kernel, and we ended with v is in this singleton containing the 0 vector. But that means that we've shown that the kernel of t is a subset of this singleton containing the 0 vector. So this, combined with this result right here, which essentially comes from what we did in the last proposition, gives us this forward direction. In other words, it gives us the fact that the kernel of t is equal to just the 0 vector. Okay, so now let's look at this reverse direction. So for the reverse direction, we want to suppose that the kernel of t is equal to the 0 vector, and v and w are in v such that t evaluated at v equals t evaluated at w. So that's the kind of canonical setup to start an injection proof. Okay, but now let's move some things around. Let's notice that that means that t of v minus t of w is equal to the 0 vector by subtracting t of w. Now we'll use the fact that t is a linear transformation to rewrite that as t of v minus w equals the 0 vector. But that tells us that v minus w is in the kernel of t, which is equal to the singleton containing the 0 vector. That was our assumption here. But if v minus w is in the singleton containing the 0 vector, that means that v minus w must be equal to the 0 vector. But if v minus w is equal to the 0 vector, that means v must be equal to w. But starting here and ending here is exactly what we need to prove injectivity. So all of this calculation implies that t is in fact injective. Good. And so that finishes the proof of this proposition. And now we'll start looking at some examples. Now we're going to go through a bunch of examples. And these are going to start with the most basic and simple examples. The first of which is a map Z from V to W that takes every vector V to the 0 vector. So let's check that this is in fact a linear transformation. So if we do Z of V plus W is equal to 0 because Z maps everything to 0. But that's going to be equal to 0 plus 0, and then that's going to be equal to Z of V plus Z of W, as Z of V is 0 and Z of W is 0. But starting here and ending here is exactly what we need for the additive component of this being a linear transformation. Okay, so now let's look at the other one. So let's do Z of alpha times V. So let's notice that's equal to 0 because that's all that Z does is it takes everything to 0. But 0 is the same thing as alpha times 0, which is the same thing as alpha times Z of V. So that's the second property. So these two calculations show that Z is in fact a linear transformation. Now, is it injective or surjective? Well, probably not. So it's injective if and only if V is just the trivial vector space, the 0 vector space. And it's surjective if and only if W is the trivial vector space which just contains 0. If V and W are more interesting vector spaces, then it is neither injective nor surjective. Okay, so let's look at this next example, the identity map. So that goes from a vector space to itself, and it maps the vector to itself. So maybe we'll just check one of the things here. So IDV evaluated at V plus W, that's equal to V plus W, because the identity map doesn't do anything. But that's the same thing as IDVV, and then plus identity map on W. But that's the additive condition for a linear transformation. I'll let you check the scalar multiple condition. Okay, so these are really important examples, even though they're so simple. They're always ones to keep in the back of your mind. Okay, so now let's look at some more examples. We're ready for our next two examples. So let's recall Kn is the set of n tuples with entries in K, but we write those n tuples as these columns for reasons that we'll see later. And then K, that's just the ground field. And so let's define our map as follows. So T evaluated at this x1 down to xn is a1x1 plus a2x2 all the way up to anxn. So adding things together like that will definitely get us an element from the field. So let's check maybe the addition property, and I'll leave this scalar multiplication property for you to check. So let's look at T evaluated at x1 down to xn plus y1 down to yn. So let's notice that's the standard form of the sum of two vectors from Kn. But using the vector sum rule, we can write that as x1 plus y1 down to xn plus yn. Again, that's the sum of two vectors like this. Okay, but then that's going to be exactly a1 x1 plus y1 plus all the way down to an xn plus yn by the definition of our map up here. But now we can resort some things a little bit. We can write this as a1 x1 plus all the way up to an xn plus a1 y1 plus all the way up to an yn. Again, that's just moving some things around. Maybe if we really want to, we could put some parentheses around here and here. But that first set of parentheses is exactly T evaluated at x1 down to xn, whereas this second set of parentheses is exactly T evaluated at y1 down to yn. So that's the additive property we need for a linear transformation. Again, I'll let you check the multiplicative property. And while we're at it, let's look at a very special example of this. Let's say we have T going from R3 down to R, and we would say T of x1, x2, x3 is, say, 5x1 minus 2x3, 2x2 plus x3. So that would be a really concrete example of this type of linear transformation. Okay, so let's look at this next one. It's S from K2 to K3. So those are ordered pairs to ordered triples, again, written as columns. And here what we do is just take this x1, x2 and turn it into the triple x1, x2, 0. So this is some sort of inclusion of K2 inside of K3. So in this case, let's maybe check the multiplicative property. So let's look at S alpha x1, x2. So that's the scalar multiple of alpha with this vector x1, x2. That'll be equal to S alpha x1, alpha x2. So that's by the scalar multiplication properties that we defined previously. But that's equal to alpha x1, alpha x2, 0 by the definition of F. But then that is equal to alpha x1, x2, 0. And that's because we can take this 0 and kind of trivially rewrite it as alpha times 0. And then we can factor the alpha out of all of the components. But that's going to be exactly alpha of S evaluated at x1, x2. And that's what we need for this scalar multiplication property of the linear transformation to be satisfied. So let's look at our next example. So here it's going to be a map from K2 to K2. So in other words, ordered pairs to ordered pairs. Again, we're writing them as columns, where t evaluated at x1, x2 is ax1 plus bx2, cx1 plus dx2. So let's maybe check the additive property of the linear transformation here and then determine if it is injective. So let's look at t of x1, x2 plus y1, y2. So that's a general shape of a sum of two vectors from K2. So that'll be equal to t of x1 plus y1 and then x2 plus y2 using the rule for sum of vectors that we had previously. Okay, but that'll be equal to, let's see, a x1 plus y1 plus b x2 plus y2 in this first component, and then c x1 plus y1 plus d x2 plus y2 in this second component. But now we can multiply all of this out and then reorder, leaving us with something like this. So we'll have ax1 plus bx2 plus ay1 plus by2. So that's in the first component. Then we'll have cx1 plus dx2 plus cy1 plus dy2. That's in the second component. But now we can split these up again using the rule for vector addition into ax1 plus bx2, cx1 plus dx2 is our first vector, plus ay1 plus by2, and then cy1 plus dy2 is our second vector. But let's notice that that is exactly t evaluated at x1, x2 plus t evaluated at y1, y2, as needed for this additive property to work. Again, I'll let you check the multiplicative property. Okay, let's get rid of this and then decide if this is injective or not. Now let's decide if this is injective, and we'll do that by looking at the kernel. So let's suppose that we know that x1, x2 is in the kernel of t. And so if we show that x1, x2 must be equal to the 0 vector, then it is indeed injective. If x1, x2 is possibly not the 0 vector, then it's not injective. Okay, so let's get to it. So being in the kernel of t, that means that if we do t of x1, x2, we should get the 0 vector. In this case, that's just 0, 0. But now using the rule for t, which is written right up there, we get that ax1 plus bx2 and then cx1 plus dx2 equals the 0 vector. But now vectors are equal if and only if both components are equal. I guess I should say all components, just in case there are more than two components. Okay, so that means we know ax1 plus bx2 must be equal to 0. And then cx1 plus dx2 must also be equal to 0. Now, how might we solve this? Well, we'll just do maybe some sort of combination of these two equations until we can get one of the variables by itself. So let's see if we can get rid of this x2 component. So let's maybe take this first equation and multiply it by d. We'll take the second equation and multiply it by negative b and see what we get. So that gives us the following two equations. A dx1 plus b dx2 equals 0. And then we have minus bcx1 and then minus b dx2 equals 0. Now let's add these two equations. So if we add these two equations, we will have AD minus BC times x1 equals 0. Now, as long as AD minus BC is not 0, then we can divide by it, or depending on the field, multiply by the multiplicative inverse. So let's just write that out carefully. If AD minus BC is not equal to 0, then this implies that x1 is equal to 0. And then furthermore, if x1 is equal to 0, plugging that back up here, we can see that that clearly says that x2 is also equal to 0. Now, if AD minus BC is not 0 and x1 is 0, then we get that x2 also must be 0. Again, if AD minus BC is not 0, that means B and D cannot be simultaneously 0. So one of these equations will allow us to solve x2 equals 0. So in other words, we have x2 is also 0. So what we've just proven here is that this thing is injective exactly when, in other words, if and only if, AD minus BC is not equal to 0. This kind of linear transformation and this kind of condition is something that we'll expand on a lot as we move through this material. Okay, let's do another couple of examples. Okay, so our next two examples will be linear transformations from the set of polynomials, I should say the vector space of polynomials with coefficients in k to themselves. So our first one will be called D, and it's defined by taking the formal derivative. So what I mean by the formal derivative is just the power rule because these are polynomials. And I say the formal derivative because if this field is not like the real numbers or the complex numbers, defining the derivative is a little bit tricky. Okay, so let's maybe look at an example of this. So if we do D evaluated at 3x to the fourth minus 2x squared plus 3, we'll get 12x cubed minus 4x. And that's, again, just from taking the derivative. So let's check that this is a linear transformation. So we'll do D evaluated at f of x plus g of x. But that's going to be f of x plus g of x all prime. But then we know that there's a sum rule for derivatives. So that gives us f prime of x plus g prime of x, which is exactly D evaluated at f of x plus D evaluated at g of x. So let's first of all notice that this is most definitely not injective. We can see that because this D evaluated at this polynomial is the same thing as D evaluated at the polynomial 3x to the fourth minus 2x squared with no plus 3. That's because the derivative of 3 is 0. So in fact, we can put that together just saying that the kernel of D here is going to be all constants. Maybe we would just say alpha, all alpha in K, or maybe just the field K itself because the derivative of a constant is 0. There's definitely more than 0 in that field. Okay, so now let's look at the second one. So I've said it's I, and so that's going to be the formal antiderivative, but without the plus C. So in other words, if we take I of, let's say maybe 2x plus 3, we would get x squared plus 3x. Now let's notice that this is not surjective because I of f of x is never equal to, say, a constant like the number 3. Because think about what the antiderivative does to a polynomial. It increases the degree of a polynomial. So there are no polynomials with degree -1, which is what we would need for this to work out for this 3 here. So our next 2 examples will take large vector spaces and condense them down to smaller vector spaces. So my first one, which I'll call T alpha, starts with the vector space of polynomials and goes to the ground field K. And this is called the evaluation map. So T alpha of f of x is equal to f evaluated at alpha. So let's look at an example of this happening. So for example, T3 of x squared plus 2x minus 5 will be equal to 3 squared plus 2 times 3 minus 5. So in other words, that is 9 plus 6 minus 5. That's the number 10. Okay, so let's do some examples here. So let's check the additive property for this being a linear transformation. So let's do T alpha evaluated at f of x plus g of x. So that's going to be f plus g evaluated at alpha, but that's f of alpha plus g of alpha, but that's equal to T alpha f of x plus T alpha g of x. That's exactly what we need for this additive property for our linear transformation. So let's look at another one. I've called it A underscore alpha beta. And what it does is it starts at the vector space of continuous functions. Let's recall that we denoted that by C0R, and it goes to the real numbers. And what it does is it takes as an input a function, and as an output, it gives you the integral from alpha to beta of that function. So by the standard properties of the integral, it's easy to check that this is a linear transformation because we have an addition rule for integration and a scalar multiplication rule for integration. So let's look at an example of this while we're at it. So let's look at maybe we'll take the interval 0, 3 of the function e to the x. So that's going to be equal to the integral from 0 to 3 of e to the x dx. But the antiderivative of e to the x is e to the x. That's e to the x evaluated at 0 and 3, which is e to the 3 minus e to the 0, which is 1. So this linear transformation takes the function e to the x to the number e cubed minus 1. Okay, so I think that's good for examples. Now I'm going to leave you guys with a couple of warm-up exercises. I've got 4 nice warm-up problems to leave you with. So the first is a map from kn plus 1. Let's recall that those are n plus 1 tuples with entries in k written as vectors. And the codomain here is the space of all polynomials with coefficients in k. So here we've got our vector with n components. I've labeled those components slightly differently here. I've started at 0, so a0, a1 down to an. So that vector is mapped to the polynomial a0 plus a1x plus a2x squared all the way up to anx to the n. So show that as a linear transformation and then determine if it is injective or if it is surjective. Maybe if it's not surjective, can you tweak the codomain to make it surjective using one of the examples of subspaces that we had in the last video? So now let's repeat this problem. In other words, decide if it's a linear transformation and answer the injective-surjective question for the map from kx to kx defined by t evaluated at f of x is f prime minus x times f of x. Okay, then I've got 2 more that are about arbitrary linear transformations in vector spaces. The first is to show that the composition of 2 linear transformations is also a linear transformation. And while I'm at it, I use some slightly different words here. Notice I use the word linear map. Well, often we'll use the word linear map instead of linear transformation. So it's important to keep that in mind just in case you're reading different texts. Okay, so just we've got t from v to w, s from u to v. Then that means t composed with s goes from u to w. And you want to show that's a linear transformation given these first 2 are as well. Then the last problem has to do with the sum of linear transformations. And in this case, you need to start with 2 linear transformations with the same domain and codomain, so v and w in this case. And then you'll look at their sum. So T1 plus T2 show that that's also a linear transformation. Okay, that's a good place to stop.